Hello, this is the second episode of our series on stochastic calculus for beginners. Today we will answer the question, why a new calculus is needed for stochastic processes. And the answer lies in this mysterious-looking equation, dwt squared equals dt. The results of this video was first obtained by the German-French mathematician Wolfgang Doeblin, also known as Vincent Doeblin in French. He lived a very short but productive life. I encourage you to look up his bibliography, two links of which are in the description. And before we begin, I would like to ask you why you are interested in stochastic calculus. Are you interested in the subject for its own sake, or do you have any particular fields of applications in mind? With that said, let's get on with the main topic. In the previous episode, we defined the Brownian motion, a continuous time stochastic process. As a recap, here are its defining properties, which we will use extensively. The Brownian motion has an initial position of 0. Its sample path is almost surely continuous. Its increments are stationary and normally distributed, with zero mean, and the variance equals to the length of the time interval. And lastly, we have the independent increment property. Increments over non-overlapping time intervals are statistically independent. Also, in episode 1, we defined the main object of study, the Ito integrals. They have the following form: the integral of xs dws from 0 to t. The key in Ito integrals is that the integrand x of s is evaluated at the left endpoint in each subtime interval. And we assume that the integrand x of s is non-anticipating relative to the Brownian motion w. That is to say, at each time instance, the value of x of t is independent of the future of the Brownian motion. And last time, we integrated a deterministic function. So today we will see what happens if x of s is a random process, from which it will be clear that a new calculus is called for. As our motivation, let's evaluate this innocent-looking integral using definition. The integral of ws dws from 0 to t. Let's first try to simplify the Riemann sum, the sum of wi minus 1 times delta wi. Recall that the notation xi minus 1 is a shorthand of xti minus 1. Consider the identity wi squared equals wi minus 1 plus delta wi quantity squared. This is just the definition of delta wi. Expanding the square, we get wi minus 1 squared plus 2 wi minus 1 times delta wi plus delta wi squared. So we can isolate the term in the summation, wi minus 1 times delta wi, which reads 1/2 wi squared minus wi minus 1 squared minus delta wi squared. Summing over I, we obtain an expression for Sn, in which there are two sums, the sum over I of wi squared minus wi minus 1 squared, and the second sum, the sum over I delta wi squared. The first sum simply telescopes and reduces to wn squared minus w naught squared. But we know wn is the same as wtn, which is the Brownian motion at the final endpoint, so it's just wt. And w0, by definition, is 0. So the first sum is just wt squared. This is independent of n. But what about the behavior of the second sum? This is where things gets really interesting. Notice that algebraically, the second sum cannot be simplified further. So perhaps we can say something about its distribution. Delta wi are increments of the Brownian motion, which are independent random variables due to the independent increment property. They are also normally distributed, each with mean 0 and a variance of delta t, the length of the time subinterval. So Qn is the sum of squared IID Gaussian random variables. And we know from basic probability that Qn is a scaled chi-square distribution with n degrees of freedom, delta t times chi-squared. A chi-square distribution has its mean equals its own degrees of freedom, and the variance equals twice the degrees of freedom. So we can easily obtain the mean and variance of Qn. The mean of Qn is delta t times n, but that's just t. And the variance of Qn is 2n times delta t squared. which is 2t delta t. As we can see, the expected value of Qn is independent of n, and the variance of Qn, which is linear in delta t, tends to 0 as n tends to infinity. So this means the mean square limit of Qn is t. The mean square limit was introduced in the first episode. And here's a recap of the definition. Let xi(n) be a sequence of random variables, and let xi be a random variable. We say that xi is the mean square limit of xi(n) if xi(n) and xi all have finite second moment, and the L2 distance between xi(n) and xi tends to 0. That is the expected value of xi(n) minus xi, absolute value squared. And the results of our calculations earlier implies that the L2 distance between Qn and t tends to 0, and therefore Qn converges to t in the L2 sense. What's interesting is, for any finite n, Qn is a non-degenerate random variable, but it converges to a non-zero deterministic function t. And here's the visualization. Some of the densities of Qn. Since Qn follows a scaled chi-square distribution, its density have a closed form which we can easily plot. Here I pick t equals 1. As n gets larger, the density gets more and more concentrated around the value of 1. So that's the visualization of the convergence of Qn. Qn tends to t as n tends to infinity in the mean square sense. So combining our results, the first term in Sn is half Wt squared, and the second term converges to minus half t in the mean square sense. So by the definition of Ito integrals, the integral from 0 to t ws dws is 1 half Wt squared minus half t. But hold on, this does not look like regular calculus. If we use the chain rule, or equivalently the U substitution from regular calculus naively, we would get half Wt squared. But in the actual result, there is minus half t at the end. So what is going on? Well, the minus half t term comes from the second sum, the sum of second order increments delta wi squared. So why does the rule of regular calculus not have this extra term? To see that, we have to go back to calculus 1. Let's integrate the function x from 0 to 1. By definition, as usual, we partition the interval 0 to 1, take the left Riemann sum. The area is the total area of the little triangles, so it's the sum of half delta x squared, that's half delta x. The coefficient 1/2 matters little here. The point is the error is linear in delta x, which tends to 0 as n tends to infinity. The moral of the story is, in regular calculus, the second order contributions tends to 0 as the partition becomes infinitely fine. Let's do a detailed re-examination of the U substitution in basic calculus. So consider a smooth function g of t. We all know that the integral of g of s dg of s from 0 to t is half g of t squared minus half g of 0 squared. Let's review why this works. And what we're about to do is essentially a proof in real analysis. And don't worry, if you don't have a background in real analysis, that's not part of the prerequisites of this series. I will walk through things very carefully. Let's take the left Riemann sum of the integral, but the same identities which we use for w still holds here. That's just plain algebra. The first term still telescopes in the same way, and it remains to show that the second term tends to 0 as n tends to infinity. To show that, let's first use the mean value theorem. The mean value theorem states that for a smooth function g, this finite difference in g is g prime of ci times delta t, where ci is a point between ti minus 1 and ti. And next we use the extreme value theorem to bound g prime. The extreme value theorem says a continuous function on a closed and bounded interval must be bounded. In fact, EVT is stronger than that. It states that the continuous function also attains max and min. But that does not concern us here. All we need here is a bound. So we assume g to be a smooth function, so g prime is continuous. So g prime absolute value is bounded above by m for some positive constant m over the entire interval. And our next step is perhaps the most common technique in analysis. That is to use the triangle inequality to obtain an upper bound. The first step is substituting delta gi squared. using the equation given by the mean value theorem. And next, we use the triangle inequality. The absolute value of a sum is no greater than the sum of the absolute value. And then we use the bound for g prime. So the whole thing is bounded above by the sum of m delta t squared, which is a sum of constants that equals mt times delta t. So as n tends to infinity, delta t tends to 0, and therefore the sum of delta gi squared tends to 0. The second order contributions of the increments in g tends to 0. And this is why we never see an expression of the form the integral of blah 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 dx squared in calculus. The second order contributions of dx squared simply vanishes. And that's why in applied sciences and engineering, when you see a second order infinitesimal, you neglect it. Because in the integral, its contribution does not matter. And this is a rigorous math proof. And this concludes the proof of the formula. Going back to the main proof, we can see that the mean value theorem and the extreme value theorem plays a major role here. The mean value theorem allows for linear approximations of the function g, and it rests on the assumption that g is smooth. The extreme value theorem, on the other hand, bounds the derivative. None of those things are true for Brownian motion. Recall, the Brownian motion is nowhere differentiable. As we showed in episode 1, if we try to evaluate the derivative of the Brownian motion, we end up with a normal random variable with infinite variance. So the derivative does not exist as an L2 random variable. And that's why the sample paths of Brownian motions are infinitely jagged. They look extremely rough. So clearly we can see that the mean value theorem doesn't work for Brownian motion. And that's why the non-differentiability of Brownian motion prompts a new calculus. The ordinary chain rule will be replaced by the so-called Ito's lemma, aka the Ito-Doeblin formula, and the product rule is replaced by Ito's integration by parts. And these are topics of future videos. And here's another reason why the extra minus half t term must be needed. It has to do with a general fact about the Ito integral. The Ito integral should always have zero mean. And that's because in the assumption of the Ito integral, xt is non-anticipating relative to wt. The function xt at any instance contains no information about the future of the Brownian motion wt. To put it more precisely, if time s is before time t, the random variable xs and the increment wt minus ws of the Brownian motion are statistically independent. We will derive eyt equals 0. Before doing so, we remark that this is a consequence of a property of yt known as a martingale, which is a type of stochastic process that models a fair game. We will discuss martingales in greater detail in future videos. And here's the heuristics why Ito integral should always have zero mean. Remember, at time step i-1, delta wi is unknown. That's a future increment. So therefore, xi-1 and delta wi are statistically independent. So if we take the expectation of the Riemann sum, the expectation of each term factorizes, and because delta wi has zero mean, the sum is just 0. And take n tends to infinity, e of yt is also 0. And let's check whether this is true for the integral we just calculated. Since wt is normal 0t, the expectation of wt squared is simply the variance of wt, which is t. And that's exactly what we needed. The right-hand side vanishes. Without the minus half t term, the right-hand side is just half wt squared, which is non-negative, and therefore its mean is also non-negative, which would violate the general property of the Ito integral. Its mean should always be 0. And finally, with all that preparations, we're now getting into the heart of Ito calculus. We just showed that the second order sum of the Brownian increment converges to t in the mean square sense. So it seems suggestive to write this as the integral of dws squared from 0 to t equals t. And if we formally apply the fundamental theorem of calculus by taking differentials on both sides, we get dwt squared equals to dt. And that's the mysterious looking equation we were talking about at the beginning. The question is, how do we interpret this? It cannot mean literally that an infinitesimal increment of the Brownian motion squared is a deterministic infinitesimal dt. It has to be interpreted in an integral sense. And here's the statement. Consider g of s to be a non-anticipating function. whose second moment has an upper bound for all s in the interval t0 to t for some positive constant m. Then we have this formula. The first part of the formula is a definition, and the second part is a theorem. The integral of gs dws squared from t0 to t, which is defined as the mean square limit of the sum over I, gi minus 1, delta wi squared. Notice that in this definition, in the second order stochastic integral, so to say, g is also evaluated at the left endpoint. This is exactly the same as the definition of Ito integrals. And the theorem part of this formula says this mean square limit equals the integral from t0 to t gs ds, where ds is an ordinary differential from standard calculus. And in short, by comparing the first and final expression, we write dwt squared equals dt. And this formal identity is always understood in the sense above. Let's look at the proof. First, put the integral on the right-hand side as a limit of a Riemann sum. The limit of the sum over I, gi minus 1 delta t. Let's consider In, the difference between the sum on the left-hand side and the one on the right-hand side. And we wish to show that this In converges to 0 in a mean square sense. That is to say, the expected value of In squared tends to 0. Expansion gives the square terms and the cross terms. All the square terms form the first sum, and the second term is the sum of all the cross terms. This looks rather complicated, but don't worry, taking the expectation simplifies things drastically. Remember, g is non-anticipating, and here I is greater than j. In the first summation, it is clear that gi minus 1 squared and delta wi squared minus delta t quantity squared are statistically independent. And in the second summation, notice that gj minus 1, gi minus 1, and delta wj are all to the left of delta wi, and therefore we have these two box terms independent. And if we take the expectation of In squared, those independent terms factorizes. But to take expectation, we also need the moments of delta wi. And here we just give the formulas. The derivations is in the last part of this video, called the lemma moments of Gaussian. The expected value of delta wi squared minus delta t quantity squared after expansion simplifies to 2 times delta t squared. Since the expectation of delta wi squared is delta t, the cross terms all vanish, so we're just left with the pure square terms. And the expectation of In squared becomes the sum of e gi minus 1 squared times 2 delta t squared. And here, because we assume that g has bounded second moment, this is less than or equal to the sum over I m delta t squared. But look at this sum. This is the exact same sum that we seen earlier of the proof that the integral of blah 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 dx squared is always 0. So therefore, the expectation of In squared tends to 0. Hence, 0 is the mean square limit of In. Rearranging, we get the mean square limit of the second order sum is the mean square limit of the sum over I gi minus 1 delta t. And of course, this is the regular Riemann integral, the integral of gs ds over t0 to t. So at this point, we finally understand the meaning of this identity, dwt squared equals dt. As promised, let's finish the lemma, moments of Gaussian. The moment generating function mxt of an arbitrary random variable x is defined as the expected value of e to the tx, provided the expectation exists. And it's a well-known fact that for normal 0 sigma squared random variables, mgf is e to the 1/2 sigma squared t squared. And then we're just going to Taylor expand these two formulas and compare their coefficients. And here we are hand-waving by interchanging the summation and the expectation without additional justification. And specializing k equals 2 and 4 gives us the moment we needed in the last proof. That's it for today's video. If you enjoyed the content, please consider like and subscribe. And I'll see you next time. Bye.